Hello everyone, I am Gu Yu from Shenzhen University. I'm very glad to take the presentation in ACM 6 Special. Today, my presentation is collaboratively inspect large area silver pipe networks using pipe robotic capsules. The first part is the introduction. What is urban silver pipe network? It is an important infrastructure in cities, and it undertakes the water transportation and circulation. However, they are buried underground and surrounded by soil, so they are prone to pipe faults, just like the cracks and erosion. These pipe faults may cause some accidents. For example, in October 2021, this fault caused the pipe leakage and the serial road collapse in Shenzhen. So we need a well-rounded and a periodical inspection for the network. It has some features. The network has a huge pipe millage in a lot of cities, and the pipes provide all-day service for citizens. Its circumstance is narrow and obscure. Finally, the pipes are vulnerable because of their materials. There are a variety of sensors are used for the pipe inspection, such as the laser, the infrared, and the ground radar. They have respective merits and demerits in different inspection scenarios. And for the capture data, in the past, workers used the artificial visual judgment to recognize the pipe faults, but it is labor-intensive and unreliable. And currently, the signal and the image processing and the machine learning are applied effectively in the fault recognition. For example, CCTV is the most widely used technique for pipe inspection. It has some merits, but also has some limitations, such as the pipe harm, the service disruption, and the slow inspection. Our group invent a capsule, robotic capsule for the inspection. It is low cost and mini-sized. The camera could capture the inner wall images of pipes, and the light could provide light source in pipelines, and the IMU could locate the pipe faults in the network. Moreover, it has a flexible and safe inspection process. Just like these figures, capsule could flow with water, and the workers could drop and salvage these capsules in wells. So there is no pipe harm and service disruption. There are two research problems for the robotic capsules. The first one is the inspection process is flexible, but it's not efficient. So we arrange multiple workers collaboratively inspect the pipes using robotic capsules to improve the process. And the next one is how to process these capture images. We use the deep learning to recognize pipe faults because the method is big data driven, and it is accurate in image classification. The next part is the proposed collaborative inspection. The workflow includes 5 steps. The first step is inputting the geodata and the inspection resource, the capsules and the workers. Next, solve the collaborative scheme, and according to the scheme, we could capture the pipe images. Using the images, we could recognize the pipe faults with deep learning. And finally, all the pipe faults could be located and visualized in the network. So what is the collaborative inspection? Firstly, multiple workers drop and salvage multiple capsules at the same time. It could enlarge the inspection scale for a large-scale network. And each work could salvage and capsules which dropped by others. This collaborative approach could promote inspection efficiency. We established a mathematical model to describe the problem. The objective functions have 5 items. The minimum workers travel distance, waiting time, the lead time, as well as the maximum pipe inspection degree and the proportion. Next, we use the meta-heuristic algorithm to solve the best solution. The neighborhood searching could explore the wider neighborhood for better solutions. And the simulated annealing could help the neighborhood searching jump out the local optimality for a global optimal solution. According to the scheme, we could capture these images, and we found them are tremendous, and they have complicated texture and background. Especially, there is a remarkable class imbalance among the normal and false images. It will cause the difficulties in the classification. So we use deep learning network, the ResNet, and the class-weighted cross-entropy to classify these images to recognize the faults. Next one is the case study and results. The experiment is held in Bao'an district of Shenzhen in China. The pipelines are about 22 meters length, and there are about 600 pipelines. Their building yields, materials, and diameters are different. Moreover, the pipe network covers traffic, arteries, resistance, and the commercial centers. So it is indeed a large-scale and complicated network. We use 4 workers and 10 robotic capsules to complete the inspection task. And finally, there are about 11 kilometers pipelines are inspected successfully. The collaborative inspection, just like the special temporal trajectories of workers. For worker S1, he drops 2 capsules and salvage 4 capsules. However, among these capsules, the capsules 9 and 6 are dropped by himself, while the 8 and 7 are dropped by others. Let's see. This is the cooperation in collaborative inspection. We also find, compared with the naive scheme without cooperation, the collaborative inspection scheme could improve the consumption on working time and traveling distance of workers. Besides, due to the collaborative approach, their waiting time decreases very much. According to the scheme, we could capture these images, and after the extracted and screened, there are about 1100 images used in the classification, and there are 4 types of faults: the crack, intrusion, obstacle, and drop offset, joint offset. just like these figures shows. We use the ResNet to recognize these pipe faults, and it gets a well performance. Its overall accuracy is 0.92. To be noticed, we also find some error predicted samples because they have complicated and easily confused texture, and their fault objects are tiny. So we think the phenomenon is inevitable and acceptable. Finally, these pipe faults could be located and visualized in the pipe network. This collaborative inspection has been applied in some practical applications in Shenzhen and Zhejiang province. Finally, is the conclusion and the outlook. Present inspection techniques are various, but still have some limitations for the urban sewer network. And our proposed collaborative inspection recognize 33 pipe faults with a good accuracy of 92% in a large-scale pipe network. And we have an outlook. We think in the future, the data capturing by sensors, the force recognition, the force recognition, and the force location will be combined into IoT. That to see it could promote the intelligence of the pipe inspection and timely support the pipe maintenance and its administration. Okay, thank you very much.